Okay, hello, and thanks for the invitation. So I'm going to describe some work that I've done over the last year. Most of it will be this recent paper with John Collins and Nobuo Sato, a few other comments. So there will be basically three themes of this talk, three things I want to discuss. First is to explain the original motivation for this paper that I'm mostly going to be talking about. The original motivation was to contrast two different ways of talking about the divergences that appear in factorization derivations, what we call track A and track B. So here I'm going to start with track A and explain what I mean by that. Um, I'm going to then address the question of whether the contrast between these two different ways of discussing factorization are actually matter for practical situations. That'll be getting into the positivity issue, positivity of parton densities. And finally, I'll try to make some connection with TMD PDFs and TMD correlation functions. So I'm going to begin by talking about, or I'm going to describe what I mean by track A styles of factorization derivations. So in track A, what I mean is that we start by specifying a definition, an operator definition for something like a parton density. And for now, I'll just discuss sort of standard collinear unpolarized parton densities like what we have in DIS. You can try just using, say, a number density definition, the naive number density definition, but then you find, of course, that it's got ultraviolet divergences. There are no collinear divergences because QCD is an infrared finite theory, but you have to deal with the UV divergences in some way. And you can deal with them at least in the track A approach that I'm discussing here. You deal with them just by doing a kind of renormalization, just basically a standard way of doing renormalization. So again, let me write down an expression for a bare PDF. You notice that I've got 0 subscripts on these operators for the fields to indicate that they're bare fields. And then the way you get something finite, UV finite, is to take this bare field, which is UV divergent, and rescale it in the generalized sense of a factor with a convolution, rescale it with a factor that removes the UV divergences. So you end up with a definition for the PDF, and then you can construct factorization theorems by just making sure that as you consider all momentum regions that can contribute to a process, you remove any overlap with what you describe with the collinear PDF. Okay, so then the idea is we want to contrast that with this other way of thinking about setting up factorization, which we've called track B factorization. And let me just explain what I mean by that. So there, what you would do is you take a typical kind of process like deep inelastic scattering, and you start by basically postulating a factorization. So up here at the top, I've basically got the cross-section factorized into what I call a bare PDF and a massless partonic cross-section. So you write this down, and then you observe that a massless partonic cross-section comes with collinear divergences. So then what you do is you observe that you can take this massless partonic cross-section and write it in another factorized way where you factor out the 1/epsilon poles. I'm thinking of everything here in dimensional regularization. 1/epsilon poles, so a divergent contribution that I label by C here, convoluted with now a partonic cross-section that, in a sense, has been made finite. So you've pulled out the divergent parts. So the top line then becomes like this. And then you simply define the parton density to be this thing that you call the bare PDF up here with those divergent 1/epsilon poles, the collinear divergences absorbed into the PDF, the definition of the PDF. And then, of course, you have an expression for the cross-section, which involves the final PDF, what we might call the renormalized PDF in the track B approach, convoluted with something finite. So this is another way that one often hears these things discussed. And notice that I've put a subscript with a little b here. That's to indicate that this is a track B bare PDF. and contrast that with the A superscript over here. This is a track A superscript, because at this stage, it shouldn't be clear that these are actually the same object. So to summarize, we assume that there exists something that there exists a factorization with something we call a bare PDF, and that we can get the renormalized PDF by absorbing collinear poles into it. Some things to point out. The main thing to recognize is the lack of a derivation for this first line up here. That's where if something creates a tension between track A and track B, that's probably where it's going to be. And in particular, that bare PDF doesn't come with a specific definition. If we set things up in this way, if we state things in this way, we should be asking about what the definition of this object is. It's natural to ask if we can get some consistency between these two approaches by trying to reverse engineer what this bare PDF from the track B approach actually is, in terms of operator definitions. And that's one of the things that we did in this paper. So you can basically work backwards and say, let's insist that the factorization theorem holds. So let's say that this is a true factorization theorem, meaning that this is going to be the massless partonic cross-section, and this is going to be a physical DIS cross-section, and require that the 1/epsilon poles get reabsorbed in the way described here. And we can construct a UV renormalization prescription that gives a PDF that obeys this set of steps. And if you do that, you actually get something that's kind of like the BPHZ scheme of standard renormalization. So that gets rather technical, and because of the short time, I won't go into it. But the upshot is that you end up with a PDF, and at least at low orders, it looks like it comes out to be the same as, say, the MS bar PDF, which is good. And actually, if you get that, you might be, well, it's fair to ask whether there is any reason to worry about this distinction between track A and track B. If we end up with the same answers, and in fact, the prescription here reproduces hard coefficients, perturbative calculations, just as well as, say, a track A approach. And so this distinction might look rather pedantic. So we can ask, if we just take this track B and use it as an algorithm for getting hard coefficients and so on, is there really anything to worry about with regard to practical differences? So that's going to bring me to the positivity issue. So by positivity, I mean, can we say within a certain scheme like minimal subtraction or modified minimal subtraction, that parton densities have to be positive? And that's important, of course, for phenomenology, because, well, it'd be nice if we could impose conditions like that when we're say extracting PDFs. Well, we need to know if that's a reliable thing to do and if it's consistent with the theoretical setup. And in fact, there are arguments basically based on the track B methodology that seem to show that parton densities defined in an MS bar scheme have to be positive everywhere, basically. I'll just give the reference right here. So now you should be asking, well, if the MS bar parton densities are basically the same in a track A and a track B approach, okay, some technical differences, but if they're basically the same, how is it that in one approach we find that parton densities can be positive, but in the other approach we might find that they can become negative? So we'll see how that works here in a second. One way to test a claim like this is to just do specific calculations. And for that, you can note that most of the setup, factorization and all that sort of stuff, doesn't rely on specific properties of QCD, but just the general things like renormalizability, the nice properties that you want in a quantum field theory. So we can stress test some of these claims by looking at a theory where we can actually calculate everything, something that has a renormalizability, is finite range, et cetera, just like in QCD, but where we can calculate everything explicitly with and without factorization and see how it works. So that's what we did. And basically what we did was calculate deep inelastic scattering in a Yukawa field theory. Here are the diagrams that you would have, calculating it at lowest order in the coupling. So actually we've got two fermions, one that we call the the hadron in this analogy, one is the quark in this analogy, and then there's a kind of scalar gluon. So it looks kind of like a spectator diagram, at least in the first diagram. And the nice thing is we can calculate, say, the structure functions, the DIS structure functions exactly. And we can also do it with the steps of factorization applied. So we can look at the definition of the PDF as it's calculated and so forth, and see how that affects things, right? See, does the PDF actually go negative, and does that have any effect on the, say, the observable structure functions? If you do that, here I'm going back to that previous slide, just to remind you of the definition of the PDF. We can calculate the PDF directly in this theory to low order. And we can imagine that the theory has a coupling that is so small that the lowest order is all that matters. We can also do the steps for factorization, and this is what you would get for the structure function F1. So you see the various parts highlighted here. Here's a hard part. This is all for x Bjorken less than 1, of course. And here is a parton density, and this is the parton density here on the second line that follows from the operator definition up here. And it's actually also the track B parton density if we use this kind of BPHZ type of scheme. We can then compare the F1 calculated in this way with the exact F1 calculated from these graphs. And I'll do that in just a second. But first of all, we can look at the parton density as a function of momentum fraction. So here's the momentum fraction. See, this is the parton density for the quark inside the hadron. And with moderate, but basically reasonable scales, hard scales that are sort of at the border, sort of DIS level scales at the border between perturbative and non-perturbative. And you can see that there's no problem with having the parton density go negative in certain regions. And on the right side, actually, we use this other scale, which is common for trying to push calculations to larger Bjorken X. So you can use a scale that's more closely related with the cutoff on transverse momentum that comes with a 1 minus x. And that even makes the negativity problem worse if you go out here to large momentum fractions. And by the way, this is all for mass scales that are sort of typical hadronic mass scales. So I put them up here in the corner. And then down here in the bottom, we compare the factorized calculation of the F1 structure function with the exact calculation. So the exact calculation is the solid, the dashed lines are the factorized approximations. And so you can see the region of Bjorken X, this is now plotted versus Bjorken X. You can see the regions of Bjorken X where the factorization basically starts to break down. And the point of showing that is to highlight that there are regions where you still basically have pretty good agreement between the structure function calculation and the exact and the factorized calculation, but the PDFs can be negative. Okay, so that brings us back to the question of, well, if we seem to get the same PDFs in these, numerically in these two approaches, then why would it seem that track B implies a property like positivity? So what it comes back to is the lack of a definition for this bare PDF quantity in this track B approach. Now, if you say bare PDF, it's tempting to think that you're talking about a PDF that retains all of its naive parton model type of properties, just a number density. But an actual bare PDF, we mentioned, has the UV divergences in it. And so a bare PDF is not going to be necessarily something that is consistent with parton model expectations. It's going to inherit whatever sort of odd, non-intuitive properties there are in the regulator. In the case of dimensional regularization, the regulator itself violates positivity, which is easy to see with a few examples. I mean, the most famous one is the vanishing of dimensionless integrals. The more interesting ones are like the one I give here, where you can see that the integrand is positive everywhere, but when I integrate over everything, I get a definite negative number. So the bare PDF itself actually violates positivity. And so what happens in the track B approach, if we go back up here, the way that a positivity argument would go is you'd say, well, this is a bare PDF, and therefore I'm going to assert positivity for it. And then I can look at the divergences inside of the massless partonic cross-section. And if I can argue that the divergences are positive, and I absorb positive divergences into the bare PDF, then the normalized, the final PDF that I put in the cross-section should then still be positive. But this, of course, relies on this first assertion that the bare PDF here needs to be strictly positive. But you can see that if you actually use dimensional regularization to define this bare PDF, it's going to violate positivity on its own. So that's essentially the reason. Now I'm going to turn to the last thing that I want to talk about, which is to note that there are other schemes where you really can force positivity. So for example, we can take a parton density that's a TMD parton density in the Yukawa theory, in the Yukawa theory calculation that we used as our example. That would be just the integrand of this integral right here. And instead of defining the collinear PDF through a renormalization scheme like MS bar, we could define it to be what you get when you integrate over all the transverse momentum inside the TMD PDF like this. Now you can see that this would always be a positive collinear PDF. And all I'm doing is cutting it off. To convert that to MS bar, you could subtract this term, which would be basically equivalent to subtracting the 1 over epsilon whole. And now you can see why that would give you a negative parton density. It's essentially a over subtraction. If the cutoff is much larger than the renormalization scale, I'd essentially be I'd be subtracting a large number. One thing that I think, and this is something I'm working on now that's interesting to explore, is the possibility of using collinear PDFs or similar objects defined within this kind of cutoff scheme. And one reason to do that, I think now we can sort of see with this positivity issue, is that those definitions tend to retain many of the parton model hadron structure type of interpretations that we actually would like to use, especially if we're trying to study hadron structure. Something that I don't have time to mention, but which recently has been observed, is that collinear PDFs defined in this way help with the matching between a TMD description of small transverse momentum and differential cross sections and the collinear description that you hope to get at very large transverse momentum. Now, there are complications that come with cutoff definitions. For example, everybody knows now that TMD PDFs have to be dealt with taking into account their light cone divergences, and those types of effects don't exactly cancel in a cutoff definition of a collinear PDF. And there are other things that can come up. So this is still something that needs to be looked at. I've got some comments of my own that I'll just leave a reference to here. But with that, I think I will end with what I'm going to talk about today. So let me just summarize. So what I hope to have explained was what I mean by the difference between these two approaches, what we call track A and track B in that paper. We argue that the track A is the more rigorous and well-defined of these approaches, but both are seen throughout factorization literature. Try to argue that positivity is not a general property of MS bar renormalized PDFs. Now, it tends to be obeyed when scales become very large, but if you're sort of in the borderline region, that is something that needs to be taken into account even phenomenologically. Then I tried to introduce the idea that maybe we can confront some of these issues by switching to PDFs with a cutoff definition of TMDs. So with that, I think I will end and thank everyone once again for the invitation.